This is the complete orbit determination process using 24 hours of Kiruna tracking data for Sentinel-1A. Starting from mission parameters, we generate an initial Keplerian state to seed the analysis in ODTK. Every analysis in ODTK begins with a scenario. The scenario defines the mission's temporal and environmental context. Here, we create a new scenario called Leo_tracking and set the start time to March 14, 2017 at 12 o'clock UTCG. Since the default Earth orientation parameters and space weather files don't cover this period, we update the EOP and flux data to ensure accurate Earth rotation and atmospheric modeling. With the scenario configured, we ingest tracking data in generic observation or GOBS format. We load the Leo tracking dataset under measurements. These observations from Kiruna will drive the orbit solution. Finally, we import the STK tracking system. The tracking system groups ground station into a unified network, simplifying measurement management and ensuring consistent station modeling. Before estimation, we preview measurements in the message viewer and generate a measurement times by type graph to confirm tracking coverage and data quality. Next, we insert the Sentinel-1A satellite, define a Keplerian state at the scenario epoch, input the initial orbital elements and assign the tracking ID with the satellite tracking stations and measurements defined. The next step is to perform orbit determination. In ODTK, this is done using the filter object. We insert a new filter called Leo filter. The filter processes the observational tracking data and performs sequential estimation to refine the satellite's orbit over time. Using these measurements, the filter estimates the spacecraft state and generates information that can later be used to produce ephemeris data for downstream analysis. Next, we configure the filter outputs. Within the filter properties, we enable smoother data .generate, allowing smoother data to be produced for later post-processing. To understand exactly what the filter is estimating, we use the state content tool. This utility displays the parameters included in the filter state, such as position, velocity, and other dynamic parameters that may be estimated during the solution process. This verification step ensures that the correct parameters are included before running the orbit determination. Now we execute the filter. It propagates the state forward, incorporating measurements and updating both the estimate and covariance. Once complete, we review the residual ratios graph. These ratios show measurement residuals normalized by expected uncertainty. Ideally, about 99% should fall within +3 sigma. Since several values fall outside this range, we inflate the initial orbit uncertainty, increasing radial, in-track, cross-track and velocity sigmas, and rerun the filter. However, convergence does not improve, indicating the issue lies with the initial state estimate itself. To improve initialization, we load a two-line element set, or TLE, for Sentinel-1A. Using the initial state tool, we select the TLE file as the orbit source and generate a refined starting state. After reviewing the updated state, we rerun the filter with this improved initial condition. Next, we generate residual ratios and position uncertainty graphs using the static product builder. The residuals now show improved convergence, and the position uncertainty behaves more realistically over time. Because we had previously inflated the initial uncertainty values, we now reset them to nominal levels, restoring the radial, in-track, cross-track and velocity sigmas to their default settings. After rerunning the filter, the position uncertainty graph shows significantly lower uncertainty at the start of the time span, reflecting stronger confidence in the revised initial state. The filter generates a rough file which feeds into the smoother. While the filter estimates forward in time, the smoother runs backward, incorporating information from both past and future measurements. This bidirectional processing reduces ephemeris discontinuities and folds measurement covariance into the solution. We run the smoother, producing a semtron file and refined ephemeris output. Generating the position uncertainty graph for the smoother shows a clear reduction in uncertainty compared to the filter alone. To validate modeling integrity, we perform a filter smoother consistency test. The smoother, having access to more information, should produce a smaller covariance ellipsoid. If the smoother state lies outside the filter covariance ellipsoid, it indicates modeling errors or mismodeled biases. We generate a difference file and grab the position consistency product. Passing this test is a necessary condition for a trustworthy covariance solution. Finally, we launch STK directly from ODTK to visualize the results. The filter and smoother ephemeris files are imported using the STK external propagator. These files are identical to the ephemerides generated during the filter and smoother runs, including covariance information. Opening the filtered satellite properties, we confirm that the orbit is driven by the external ephemeris file produced during estimation. To focus purely on positional comparison, we disable orbit track graphics. By turning off ground and orbit track LED types, we remove the path visualization and retain only the satellite positions in the 3D window. Next, we enable covariance visualization. Because the ephemeris files contain covariance data, STK can render 3D uncertainty ellipsoids that represent surfaces of equal probability density. The probability level is set to 95%, matching the sigma scale used in the ODTK analysis, ensuring consistency between estimation and visualization. When we view both satellites together, the smoother ellipsoid is clearly smaller than the filter-only solution, reflecting reduced uncertainty after bidirectional processing. By visually comparing the filtered and smooth states, we confirm covariance improvement and overall solution consistency. Through this workflow, we transform 24 hours of raw tracking data into a validated, high-precision orbit solution, from scenario setup and measurement ingestion, to filtering, smoothing, and covariance validation, to 3D uncertainty visualization in STK. This represents the complete orbit determination lifecycle in ODTK. Precision is not assumed. It is estimated, refined, validated, and visualized.